Okay. So in module 3, we are studying a new concept called correlation random variables, but more than random variables at a time. At first, we will discuss for paired random variables. That means bivariate data, two random variables at a time, and we are taking a sample of size n corresponding to each of the random variables. Say first random variable x and second random variable y. So all the observations are in paired format. So if you are selecting a sample of size n corresponding to each of the random variables, we will have first coordinate or pair called x1 y1, x2 y2, etc. x and yn. So we want to see whether there is any association between, any relationship between these paired random variables. And if there is a relationship, what is the nature of that relationship? And what is the degree of that relationship? And in correlation and regression, we are mainly studying whether there is a linear association or a linear relationship between these two paired random variables x and y. And we are trying to find out or extract the approximate linear relationship. Suppose the linear relationship is of the form y is equal to a plus bx or x is equal to c plus dy. Then we call the relation expressed in terms of x and expressed in terms of y. So we can express the relation as one format, y is equal to a plus bx. That means we are trying to connect our paired random variables x and y using a linear relationship, equation of a straight line. That means a slope intercept form where b is the slope and a is the y-intercept. And that is called the regression of y on x. And if we are expressing our x in terms of y, that is x is equal to c plus dy, that is called the regression of x on y. We are trying to represent x in terms of y. So y is the input variable and x is the output variable. So in correlation regression, they are called the predictor variable and the response variable. So for the first relation y is equal to a plus bx, our uh, predictor variable is x, and corresponding to every x we can have a response. So that y is called the response variable. A plus bx is called the regression line of y on x, and similarly the second one is x and the predictor variable is y. It is called the regression of x on y. So we are trying to find out the intercepts and the corresponding slopes for writing the equations y is equal to a plus bx or x is equal to c plus dy. In practical case, there may not be an exact linear relationship, but there is an approximate linear relationship. So how to identify whether there is a linear relationship or not? First of all, we can have an idea about the nature of relationship or degree of relationship by plotting these paired observations on a graph paper. Suppose we have a paired data x1, y1, x2, y2, etc., x and yn. Then we can plot this on a coordinate axis pair, x-axis, y-axis. Suppose along the x-axis we are taking the first coordinate. Suppose this is our x variable value and these are the y variable values. So corresponding to the pair xy, different dots plotted on a coordinate plane, and that plot is called a scatter plot. So by looking at the scatter plot, we can predict whether there is a linear relationship or not. If there is a linear relationship, we can see that majority of the points seems to be clustering about an arbitrary straight line. There is not an exact majority points are in the neighborhood of a straight line. Suppose we are passing a straight line through these points by connecting majority of the points, and that straight y on x. So the regression of y on x is the straight line obtained by taking x as the independent variable and y as the dependent variable. So that is called the regression line of y on x. Or similarly, you can have another diagram. So in the second diagram, see there is also an approximate that majority points are lying on the line of the form x is equal to y is equal to a plus bx. Okay, so here also we can have a regression line or an approximate regression line. Here we are taking x as the independent variable and so these are the two cases. There may be a linear relationship of the first type or the second type. No such linear relationship. There is no correlation. There is no linear correlation, or there is no linear association between the paired random variables x and y. Okay, so from the scatter diagram, it is visible that whether there is a linear relationship or not. If there is a linear relationship, we can have two types of relationship. See, in the first diagram, we can see an upward sloping scatter plot. That means if you are measuring the slope of the straight line y is equal to a plus bx, the slope will be positive slope. So that is called the upward sloping scatter plot or upward slope. So for the upward sloping regression line, as the first variable increases, as our predictor variable increases, the corresponding response variable also increases. Or in other ways, we can say that as the independent variable x increases, so that is called a direct correlation. Direct correlation means as one variable increases, second variable also increases, or one variable decreases, the second variable also decreases. That type of correlation is called direct correlation. So this is an example of a direct correlation and y, direct correlation. Okay, direct correlation or positive correlation. Positive correlation because the slope is positive. And for the second case, suppose our scatter plot is like this, majority points are clustering about negative slope. For the straight line y is equal to a plus bx, if the b value is negative, that type of correlation is called inverse correlation or negative correlation. Inverse correlation or inverse correlation. From the name itself, it is clear that why it is called inverse correlation, because as one variable increases, the second variable decreases. Okay, so that type correlation is called inverse correlation. Direct correlation, another name, it is called positive correlation. So this is called positive correlation, and this is the negative case, negative correlation. And the third diagram, no correlation. No correlation between x and y. No correlation between x and y means there is no linear relationship between the variables. No correlation. Okay, so in the first part of our module 3, we will study how to construct these two equations, y is equal to a plus bx or x is equal to c plus dy. Y is equal to a plus bx or x is equal to c plus dy are called regression lines. We have two options. You can predict y in terms of x or predict x in terms of y. If you are predicting y in terms of x, it is called the regression line of y on x. Y is predictor in terms of the input variable or the, so that is called y is equal to a plus bx, y on x, regression of y on x on y. X is predicted in terms of our y value. Okay, so these are the steps. Or paired observations. ഹലോ സ്ക്രീൻ കാണോ? ഹലോ കട്ടായല്ലോടെ?
സ്ക്രീൻ കാണാം സർ, പക്ഷെ വോയിസ് ബ്രേക്ക് ആവുന്നുണ്ട്, ഓഡിബിൾ അല്ല
സർ.
ഇടയ്ക്കൊരു കോൾ വന്നത്. ഞാൻ പറഞ്ഞ പോയിന്റ്സ് ഒക്കെ കിട്ടിയോ? അതൊക്കെയായിരുന്നു നമുക്ക് കോറിലേഷൻ ആൻഡ് റിഗ്രഷൻ. കോറിലേഷൻ പറയൂ
സർ. ഒന്ന് ഷോർട്ടായിട്ട് ഒന്ന് റിപ്പീറ്റ് ചെയ്യൂ സർ, എനിക്ക് കേൾക്കാൻ വയ്യായിരുന്നു.
പിന്നെന്താ, ഓക്കെ ആയിക്കോട്ടെ. So we are studying the concept called correlation and regression. Correlation and regression means we have more than one random variables at a time. And first we are studying two random variable case, then three or more random variable case. That is called a multiple correlation and regression. And for bivariate data, it is called a simple correlation and regression. And here we have a paired observations of the form x comma y. The first random variable is counting or measuring something, or second random variable also counting or measuring something. That means corresponding to each of the random variable values x and y, we have suppose n sample observations. Corresponding to x values, we have x1, x2, etc. xn. Then similar to y value, we have y1, y2, etc. yn. That means we can consider the paired observations x1, y1 as a first coordinate or first paired observation, and another pair observation x2, y2, similarly, etc. xn, yn. And we have these paired sample observations. And using these paired n sample observations, we are trying to develop a linear relationship. We are trying to find out whether these two random variables are related or not. Is there any connection between these two random variables? So in correlation regression analysis, we are trying to find out whether there is a linear relationship between the variables. Linear relationship between the variables means the relationship may be of the form y is equal to a plus bx. It is the straight line passing through the coordinates x comma y's, or the relation may be x is equal to c plus dy. So using the variables x and y, you can have two types of straight lines. What are they? The first one is y is equal to a plus bx, or the second one is x is equal to c plus dy. We can connect these two random variables using a linear equation or a linear relationship. Okay, so in the format y is equal to a plus b, the linear relationship where b is the slope and a is the y-intercept, we call x as the independent variable and y as the dependent variable. Or you can express our x in terms of y. If you are expressing x in terms of y, then y is the independent variable and x is the dependent variable. For the first case, y is equal to a plus bx, we are first have the value of x. So that is called the predictor variable. Okay. So corresponding to every predictor variable, you have a response. What is a response? Response is y. So y is called the response variable and x is called the predictor variable. So we are predicting y using the known value of x. So the first relation is called regression line of y on x. Clear? Similarly, you can have another regression line. You can have one more regression line. You can predict x. If we are predicting x in terms of y, the regression line is called x is equal to c plus dy. So that is the starting definition. Clear? Any doubt? So throughout our module 2, we are trying to find out whether there is a linear association, whether there is a linear relationship between the random variables x and y. If there is a linear relationship between the variables x and y, then trying to find out the relation. Then we have two choices. What are they? If there is a linear relation between the variables x and y, the relationship may be of the form y is equal to a plus bx, or it may be of the form x is equal to c plus dy. So we have two options, and one is called regression of y on x and another is called regression of x on y. And if there is a linear relationship between the variables, then we are measuring how much linear relationship is there. What is the degree of association? What is the strongness of linear relation between the variables? To measure the degree of linear relationship between the variables, we have a standard coefficient measure called correlation coefficient. So we have a formula for computing correlation coefficient, and we can see that this correlation coefficient is a number lying between -1 and +1. -1 and +1. So using that number, similar to our probability computation, using this standardized measurement, we can see whether there is a positive correlation or there is a negative correlation or there is no linear correlation. Okay, depends on the value of this R. What is R? R is called a correlation coefficient. If the correlation coefficient is positive, you can have an upward sloping scatter plot. If you are plotting the straight scatter plot on an XY plane, you can have an upward sloping scatter plot. And if there is an upward sloping scatter plot, it is called a positive correlation or direct correlation. What is the meaning of positive or direct correlation? As one variable increases, the second variable also increases. That is a concept. Or one decreases, second also decreases. That type of correlation is called a positive correlation or direct correlation. And you have another choice. What is the second choice? The computed correlation coefficient may be between -1 and 0. -1 and 0, then we can have a diagram like this. The corresponding correlation or the relation between the variables is in inverse format. As one variable increases, the second variable decreases, or one variable decreases, second increases. And that is called inverse correlation or negative correlation. And for no correlation, you can have the value of R is equal to 0. So this is the case in which there is no correlation. No correlation means that it tells us R is equal to 0 implies there is no linear relationship between the variables. If there is no linear relationship, it implies that there may be some other type of relationship. The relationship may be parabolic, or it may be cubic or sinusoidal, etc. That much relationship may be there. But R equal to 0 only guarantees that there is no linear correlation. Okay. So this is the case in which we can have the correlation coefficient is lying between 0 and 1. So this is the case for -1. Correlation coefficient lies between -1 and 0. And this is the third case when R is equal to 0. Inequality, you can have an exact value R is equal to 1. Here you can have R is equal to -1. When R is equal to 1 or R is equal to -1, we say that there is a perfect correlation. If the all the points in our data, that means x1, y1, x2, y2, etc., x and yn can lie on an exact straight line. See in the first diagram, here some points are outside y is equal to a plus bx. Majority points are clustering about the straight line y is equal to. If some points are deviating from our straight line y is equal to a plus bx or the linear relationship, we say that the correlation coefficient may be between 0 and 1, or it may be between -1 and 0. Depends on the slope of the scatter plot, or depends on the slope of the straight line fitted. Clear? If the corresponding slope is positive, you can have a correlation coefficient which lies between 0 and 1. If there is a negative sloping scatter plot, if the straight line having negative slope, you can have the value of correlation coefficient lies between -1 and 0. And for R equal to 0, there is no linear relationship. You cannot connect x and y using any of the relationship of the form y is equal to a plus bx or x is equal to c plus dy. In that case, relationship. Okay. Now we are looking at what happens when the correlation coefficient equal to 1 or exactly equal to -1. When R is equal to plus or -1, we say that there is a perfect correlation. R is equal to plus or -1. R equal to correlation coefficient is equal to plus or -1. We say that there is a perfect correlation. Perfect correlation means all the scatter plot points are lying on an exact straight line. Perfect correlation. Next, we can see an example. See the data points given by -1, 1, -1, 1, then 0, 1, 0, 1, and another point as, for example, 1, 3, and 2, 5. Suppose we have 4 sample points. The sample points are -1, 1, 3, 2, 5. Whether there is any linear relation between these paired observed variable values. The first random variable values are -1, 0, 1, 2. Second random variable values are 1, 1, 3, 5. Is there any linear coordinates x and y? Can you connect these two x coordinate and y coordinate? Can you predict some relationship how to compute the y coordinate in terms of x coordinate? Hello, Fatima, any suggestion? The points are -1, 1, 0, 1, 1, 3, 2, 5. What is the speciality of these points?
Y greater than x ആണ് sir.
Y is equal to, okay. ഇത്രയാണ് y is equal, നമുക്ക് നോക്കാം. Y is equal to എത്രയാ? Y coordinate in terms of x coordinate, x -1 ആകുമ്പോൾ y 1 ആവുന്നു, x 0 ആകുമ്പോഴും y 1 ആവുന്നു, x 1 ആകുമ്പോൾ y 5, x 2-ന് x 1-ന് 3, 2-ന് 5, അങ്ങനെ ആകുമ്പോൾ y coordinate general relationship y is equal to -1, സോറി ഇവിടെ ഒരു കറക്ഷൻ ഉണ്ട്, -1 ഇപ്പൊ ശരിയായോ? -1 ഫസ്റ്റ് പോയിന്റ്. ഹലോ വിനീത ടീച്ചർ. ആ നേരത്തെ ഒന്ന് പറഞ്ഞല്ലോ ഒരു പോയിന്റ് ഇപ്പൊ നമ്മൾ കറക്റ്റ് ചെയ്തിട്ട് -1 ഇപ്പൊ എത്രയായി? പറയാം, എന്തെങ്കിലും ഒരു സജഷൻ പറയാൻ നോക്കാം. y equal to
y equal to 2x plus 1 ആണ് സർ.
അതെ അതെ അത് തന്നെ, y is equal to 2x plus, okay good. Y is equal to 2x plus 1. That means if you are drawing the scatter plot of these 4 paired observations, we can see that all the points are lying on the same straight line y is equal to 2x plus 1. And whether that is an upward sloping or downward sloping straight line. Upward sloping or downward sloping?
Upward.
It is an upward sloping straight line. So which type of correlation we can expect? Positive correlation or negative correlation? Positive correlation. So you can expect some positive correlation. Positive correlation, and whether it is perfect correlation or not. Scatter plot are lying on an exact straight line, then your correlation coefficient is either +1 or -1. Here we can have the correlation coefficient is, because it is an upward sloping scatter plot, we have a perfect correlation coefficient, and the correlation coefficient will be
1.
So there is a positive correlation. It is a perfect correlation because all the data points, no points are deviating from the straight line. And if you are putting -1 +1, then we can see that next 3 points are lying on the straight line 2x plus 1, and the first point is slightly deviating from the line. Then you cannot have the value of r is equal to +1. So there is a deviation from r is equal to +1, and we are measuring how much deviation is there from our positive correlation 0 and 1. So suppose we have 2 sets of data, one having the correlation coefficient 0.9 and another having correlation coefficient 0.3, for which case you can expect are in the neighborhood of the approximate straight line y is equal to a plus bx. R equal to 9 case or r is equal to 0.3 case. See, we have 2 positive correlation coefficients, one for one scatter diagram or for one scatter plot. We have computed, suppose we have computed the correlation coefficient as r is equal to 0.9. And on the other hand, we have another set of data for which the positive correlation is r is equal to 0.3. And from these 2 diagrams or from these 2 computations, for which diagram or for which case you can expect more points are in the neighborhood of the approximate straight line.
R is equal
R
to
is equal to 0.9.
R is equal to 0.9. So correlation coefficient is always measuring how much or what is the degree of that linear relationship, how strong the linear relationship is. It is expressed by computing the positive correlation or simply correlation coefficient. If r is equal to +1, all the points are lying on the same straight line. Okay, if the value of r is decreases to 0, that means the points are moving outwards from, that means they are dispersing from our fitted straight line or the arbitrary straight line y is equal to a plus bx. That degree of associationship is measured in terms of a coefficient measure called positive correlation or correlation coefficient. And for a given set of data, we can measure this positive correlation or negative correlation or any answer in terms of the paired observations and their 5 different sums. So first sum is R is equal to sigma x into sigma y minus sigma xy, the whole divided by square root of n sigma x square minus sigma x the whole square, n sigma x square minus sigma x the whole square, sum of the first coordinate the whole square into square root of n sigma y square minus sigma y the whole square. So this formula is derived from the correlation coefficient definition. We are not studying the derivations. It is defined as covariance of x comma y. So we will study detailed properties of this covariance in our last module. Covariance of x comma divided by variance of x into variance of y. Variance of x into variance of y. So here we are using capital letters to indicate random variables. So we can use capital letters. Covariance of x comma y. Covariance of x comma y divided by square root of variance of x into variance of y, and this quantity is called the population correlation coefficient. For population correlation coefficient, we are using the notation rho. Rho xy is equal to covariance of xy divided by square root of variance of x into variance of y. On dividing this quantity, we can see that this rho is a number which lies between -1 and +1. And here we are using this. We are considering not the whole population. From the populations of x and y, we are selecting samples only, sample of sizes n. For first n values, that means x1 is to etc. xn, we are computing different types of sums. And similarly for the y coordinate, y1, y2, etc. yn, also computing different sums. So these sums are 5 different sums: sigma x, sigma y, product sum, x square sum, y square sum. So total we have 5, 1, 2, 3, then 5 different sums. Okay, and using these 5 different sums, we are computing the correlation coefficient Rxy is equal to sigma x into sigma y minus sigma xy divided by square root of n sigma x square minus sigma x the whole square, sigma y square minus sigma y the whole square. So we have one more n here, n into sigma x into sigma y. N is the sample size, n into sorry, there is a change in the formula. So the first quantity is n sigma xy. N into product sum, n sigma xy minus sigma x into sigma y. See, this formula is derived from this definition: n sigma xy minus sigma x into sigma y, the whole divided by n sigma x square, square root of n sigma x square minus sigma x the whole square into n sigma y square minus sigma y the whole square. You can put it into single square root. Removing the second square root. The second square root stands for the standard deviation of the y variables, so that we can extend this to single square root expression in the denominator. And see, this is the computational formula. See, the first prime variable say x takes 9 different values 50, 60, 50, 60, 80, 50, 80, 40, 70. And the second prime variable takes another set of 9 values 30, 60, 40, 50, 60, 30, 70, 50, 60. So, first of all, we are checking relationship between the random variables. So, in order to get the idea about the linear relationship, we have to plot the x coordinate and y coordinate, that is called the scatter plot. So we can see the scatter plot here. This is the scatter plot. And from this scatter plot, whether there is a positive relation or a negative relation exists between the random variables x and y. So we can measure whether there is a positive relation or negative relation. We can compute the equation because here we have taken x along our independent variable axis, y along the dependent variable axis. So the computed relation will be of the form y is equal to a plus bx. So from this diagram, can you expect a positive correlation or negative correlation or no correlation? This is the scatter plot of our 9 observations. And using these 9 observations, we can see whether there is a positive relation or negative relation. എന്തായിരിക്കും? പോസിറ്റീവ് കോറിലേഷൻ. ഇപ്പോൾ നമുക്ക് പോസിറ്റീവ് കോറിലേഷൻ സാറ്റിസ്ഫൈ ചെയ്യുന്ന ഒരു അപ്രോക്സിമേറ്റ് റിഗ്രഷൻ ലൈൻസ് വരച്ച് നോക്കാം. റിഗ്രഷൻ ലൈൻസ് വരച്ചാൽ ഇങ്ങനെ ഇരിക്കും. So this is a regression line. So in this regression line, there is exactly one point which lies on the straight line, and some points are deviating, and we are measuring how much deviation is there from the exact straight line passing through this majority points. Okay, and that will give an error estimate. And this is the straight line fitted. We can write down this straight line using some slope and intercept form. See how to compute the slope and intercept using software. We can fit this straight line. We will study how to compute the coefficients y is equal to a plus bx. So if the straight line for these 9 set of observations, you will get slope of the straight line is 0.75 and the y-intercept is 5. So the equation will be of the form y is equal to 5 plus 0.75x. For this data, you can have the relationship. For the 9 set of observations, we can see the corresponding relationship of the form y is equal to 5 plus 0.75x. Y is equal to 5 plus 0.75x. So this is our equation number 1. So this is of the form our regression line, where b is the slope, this is the slope, and this is called the intercept. Here it is called the y-intercept for regression of y on x. Clear? Then we will study how to compute this intercept and slope manually using some formula that is called the computation of regression lines. Here we are using a software called R. Using R software, you can directly compute all these correlation coefficient and the regression lines, etc. Suppose we are interested in measuring the correlation coefficient of this can see how to compute the correlation coefficient. We have a simple syntax for computing that correlation coefficient. Core of y coefficient as 0.75. So correlation coefficient is equal to 0.75 implies that 75% of observations are in the neighborhood of, not 75%, that is only measure only. 75% of observations are in the neighborhood of the corresponding straight line. Straight line with the correlation coefficient to 0.75. If the correlation coefficient is +1 or -1, then straight line we can check. We have already evaluated some x coordinate and y coordinate in our sample. What are the values? Suppose we are changing all these with our x's. What are the coordinate? -1, 1, then 0, suppose these are the x coordinates, y coordinates given by our formula 2 +1, that is -1 again, -1, then y is equal to 2x plus 1, 3, 0, 1, then 2x plus 1, 3, 3 is repeating, 0, 1, 1, 3 repeating, 2x plus 1, 5. Suppose we are plotting all these using our x comma y relationship. Then we will get another scatter plot. So this is the scatter plot corresponding to our 4 points, -1, then 1, 1, and one corresponding 1, 3, and 3, 5. Which is reverse x on y. X comma y. X is the independent variable and y is the dependent variable. So this will be the form of the correct scatter plot: -1, 1, then 0, 1, 1 or 3, and 2, 5. And if we fit a straight line to this data, we can see that see the nature of the straight line, because there is a perfect correlation. All the points are lying on the same straight line. Okay, so we have 4 different points, but all these points are lying on the same straight line. So this is the linear relationship. So in this case, naturally we can expect a positive correlation. Here, if we compute the correlation coefficient, then what will be the answer? So we are expecting the correlation coefficient as point that is equal to +1. So R is equal to 1. So if we compute the correlation coefficient using this command, correlation of y comma x, and print that R, that correlation coefficient is equal to 1. So that is there is a perfect correlation for this case. That means if the data points are lying on the same straight line with the upward sloping scatter plot, we can expect the perfect correlation. If R is equal to -1, then there is also perfect correlation, but in the opposite direction. That means inverse direction, negative sloping scatter plot. Or if the value of R varying between 0 and 1, or -1 and 0, or R equal to 0, we can have an idea about how much linear relationship is there with a positive slope or negative slope, or no such a linear relationship. So all these concepts are explained in terms of our computing correlation coefficient and finding a straight line of the form y is equal to a plus bx. Hello, any doubts? So you have to remember this formula for computation. Then in software, we have directly evaluated our correlation coefficient as 1 by just feeding all these numbers. So for hand computation, you have to remember this formula. Correlation coefficient between x and y is given by n into sigma xy minus sigma x into sigma y divided by square root of n sigma x square minus sigma x square sum the whole square into n sigma y square minus sigma y square. And that is obtained from the basic definition of computational correlation coefficient for population. For population correlation coefficient, it is covariance of xy divided by square root of variance of x into variance of y. And after computation, this coefficient measure will lie between -1 and +1. And this is a standardized measurement. This answer for any set of data x comma y, this answer will always vary between -1 and +1 only. That means the correlation coefficient cannot fall below -1 and it cannot exceed +1. So the maximum and minimum limits are +1 and -1. So all the computation of correlation coefficient vary between these two numbers, -1 and +1 only. Okay, and depends on whether it is positively signed or negatively signed or equal to 0. We can have different conclusions. So that it is positive correlation or direct correlation, negative correlation or inverse correlation or no correlation, etc. Okay, and the two types of linear associations between the random variables x and y may be of the form y is equal to a plus bx and x is equal to c plus dy. In the next class, we will study how to compute this straight line. So in the diagram, we have already seen how to draw the straight line, or we can predict a straight line for an exact relationship. If there is not an exact relationship, you cannot directly predict this answer, or y in terms of x or x in terms of y. So there is a calculation tool called principle of least squares. Using that principle of least squares, we are finding the best values of our parameters a and b, so that we are fitting a best fit straight line to our n sample size x1, y1, x2, y2, etc., x and yn, using the principle called the principle of least squares. In principle of least squares, we are always trying to minimize this error. What type error? We are trying to minimize this type of errors. See the previous case. Here there is no error because all the points are lying on the same straight line. But the situation changes if you are considering the previous case. For the previous case data, this is the scatter plot. So we are trying to minimize these type of errors. So this is the prediction line. And from the prediction line, the first point is deviated this much unit. Second point is deviated this much unit. Third, etc. Fourth, fifth, etc. And we are fitting a straight line. We are suggesting an equation of the form y is equal to a plus bx or x is equal to c plus dy, so that theoretically these differences or these deviations from the actual straight line is minimum. So that principle is called the principle of least squares. In principle of least squares, we are trying to minimize sum of squares of residual errors. See, this is the computation given by the predicted straight line, and this is the exact position. So if you are computing the exact answer minus predicted answer, there is a difference. So that difference may be that difference is called the residual or residual error, and that residual error may be positive or negative. So we are squaring and adding and minimizing. We are trying to minimize that type of errors, so that we are predicting a straight line of the form y is equal to a plus bx, and that principle is called the principle of least squares. So in the next class, we can study how to compute or how to fit a straight line to a given set of data x1, y1, x2, y2, etc., x and yn, using our principle of least squares. So that is the second part. So in examination, you can expect questions connected. That means computation of regression lines and computation of the correlation coefficients are always asked together. For a given set of bivariate data, the questions may be identify whether there is a linear relationship. If there is a linear relationship, identify that relation in terms of y on x or x on y, and measure the degree of linear relationship between the random variables. And for the first part, we are studying only for 2 random variables. Then we are extending the same idea for multiple random variables. So that is called regression. These two main concepts, correlation and regression for paired observations and multiple random variable cases. Okay, hello, any doubts?